Hello everyone. Today we will discuss about the refraction at spherical surface. So for that we need to understand a few basic concepts. The first thing is the spherical refracting surface. What it is. So spherical refracting surface is the refracting surface where the curved surface is a part of the sphere, right? So this is the curved surface of the spherical refracting surface is a part of the sphere, and this curved surface separates the two media of different refractive indices. Then we have types of spherical refracting surface. So we have convex refracting surface, and the second is concave refracting surface. So convex refracting surface is the refracting surface where the convex side is on the rarer medium side. So this is N2, this is N1. So this is denser, this is rarer, right? So you can just mention over here convex on rarer side, right? And concave refracting surface is a refracting surface where the concave side is on the rarer medium side. So here also we can draw the diagram. This is N2, this is N1, this is rarer, and this is denser. So that's why this is called as concave refracting surface. Then we have some terms related to spherical refracting surface which we have already studied in 10th standard. We just need to recall. So if we have a refracting surface, then the central point is called as pole, right? Center of curvature is the center of the sphere of which this curvature is the part. So if we say that this curvature is the part of this sphere. So you can say that this center is called as the center of curvature of this spherical surface. So this is the center of curvature of this spherical surface because this is the center of the sphere. So C is the center of sphere. from which this convex, in this case convex refracting surface is cut. Now this is center of curvature, which is denoted by C, and radius of curvature is the radius of the sphere from which this spherical surface is cut. And then principal axis. So principal axis is the line joining the pole and the center of curvature. So this is the you just need to know this. Aperture is the exposed part of the exposed part of the spherical surface. Aperture is the effective diameter of the spherical surface from where the light enters. Right? So you can say that this is the diameter of this aperture. This is the diameter. Now we have sign conventions. The sign convention is similar to the sign conventions which you have studied in 10th standard. So these sign conventions are, we know that the distances in the direction of incident ray are taken positive. Distances opposite to the direction of incident ray are taken negative. All the distances are measured from the pole, and the distances above the principal axis are taken positive. Distances below the principal axis are taken negative. So the first thing is, all distances are measured from pole, right? Then the second important point, distances along incident ray are positive. Distances opposite to incident ray are negative. Distances above principal axis positive, and distances below principal axis negative. Then we have some assumptions for deriving the expression for refraction at spherical surface. The first assumption is point object, right? Second assumption is the aperture is small. And the third assumption, which is also important, is that the incident ray refracted ray and normal make small angles with the principal axis. right? So this is also called as small angle approximation. So these were the few very important points which were required to be explained before we start the derivation for refraction at spherical surface. Now let's consider a spherical surface which is convex, right? And the light enters from rarer to denser medium. What does that mean? The object is kept in the rarer medium. So let's take our convex spherical surface. So here this is the convex spherical surface, right? So small aperture approximation you have to keep in the mind, but here I need to draw a big diagram to explain the things better, right? So this is the medium which is denser, and N2 is the refractive index of the denser medium. And N1 is the refractive index of rarer medium, right? And if we mark the center of curvature here, this is the center of curvature, this is the pole, right? And the line joining the center of curvature and the pole is principal axis. Let's extend this line, and here also. Let's keep our object here and let's mark the normal which will be the normal. We know that at every point of refracting surface, the tangent will be normal to the line joining that point with the center. Why so? If we have a refracting surface like this, right, and this is the normal, right, but in this case, this is the refracting surface, this is the center of curvature. So this part of this curved refracting surface, at any point we will draw a tangent for this and we will join this line. So radius is perpendicular to the tangent. So line joining the center of curvature with the point of refraction will always be a normal. So we can say that if we are considering that this is the point where the incident ray strikes the spherical surface. So this is your incident ray. It would have gone here in case there would have been no change of medium. But when it strikes, it undergoes refraction. Now for refraction, we need a normal at this point, and as I told you, the line joining the center of curvature with the point of refraction will be a normal. So at every point wherever the refraction occurs, this line will be perpendicular. So that means this will be actually normal, right? So this is the normal. So that means this is your angle of incidence, right? And we need to draw the arrows everywhere wherever we are showing the ray. This is your normal, so no need to show in any arrow over here. Now when it enters from rare to denser medium, what happens to the light ray? When it enters from rarer to denser medium, the light ray bends towards the normal. So that means instead of going this way, it will bend towards this normal, which is the red line in this diagram. And in this way, your diagram will be this for the refraction. So this has actually shifted towards the normal. That's why I have drawn this arrow over here. And what will be the angle of refraction? Angle of refraction will be the angle between the normal and the refracted ray. So which one is normal? Normal is this red line, and this is the refracted ray. So what will be the angle of refraction? This will be the angle of refraction. Hope this is visible. Now this is the position of the image. Right? So this is the position of the image. Now let's mark the angles made by the incident ray, refracted ray and the normal with the principal axis. So let's mark this as alpha. Angle by image with the principal axis as beta, and angle between the normal and the principal axis as gamma. Right? Now let's mark two more important points. This point I am marking as N, the point of incidence, and a perpendicular from this N on the principal axis I am marking as M. But if our curvature, this aperture is small, then the length of NM and NP will be nearly same, and this PM distance can be considered very less, so less that it can be neglected. So why this happens? We can understand it using this. Suppose this is the curvature, right? If I consider any 2 points over here which are very close over here, suppose this is the aperture. So in this case, this vertical distance and this distance will be considered same, and this separation will be very less if this aperture is very small, right? So the smaller the aperture, easier will it be for to neglect the separation. So that's why we will neglect PM, right? So we can mention over here for small aperture, Nm is nearly equal to Np and Mp can be neglected. Very important point, right? So this is the first very important step, drawing this diagram. Now the next step is, we know that if we have to write the refractive index of the second medium with respect to the first medium. How do we write? If we are writing the refractive index of second medium with respect to 1, then this is written as N2 upon N1, right? This is one thing. And also, if I want to write it in terms of Snell's law formula, that is sin I upon sin R, how will I write? I have to write the refractive index of second with respect to 1. So the angle in the opposite medium will be, I have to write for this medium, this is N2, for this medium with respect to this. So the angle in opposite medium is I, right? So I will write here sin I upon sin R. So from here, I can use these two equations. So let's mark this as 1 and this as 2. So I can mention from 1 and 2, and 2 upon N1 is equal to sin I upon sin R, and I and R are very small because of the small angle approximations. So due to this, there will be an effect that I and R will also be small. So this can also be written as sin I will be nearly equal to I and sin R will be nearly equal to R. So we can write down R N2 is equal to I N1. Very important step. Now, we have already mentioned this point that for small aperture, Nm is nearly equal to Np and Mp can be neglected. So we can write the value of tan alpha. Why do we need it? You will get to know later. Tan alpha is perpendicular upon base, that is Nm upon base is Om. So this can be written as Nm, and this Om can be written as OP, since M and P are considered very close. This is neglected, therefore N and P are very close. Similarly, we can write down tan beta. Tan beta can be written as this perpendicular upon this base. Again, m can be neglected, so we can write pi. So nm upon mi, that means nm upon pi. So again, because m and p are very close, the same reason applies here. Similarly, tan gamma is equal to nm upon mc is equal to nm upon pc, right? So this way we have these important results as equation 4. Then the next very important step is, look at the figure. If in triangle CIN, which one is exterior angle? Gamma is the exterior angle. So gamma can be written as sum of R and beta. So I can write in triangle CNI, gamma is equal to R plus beta. Therefore, R is equal to gamma minus beta. Similarly, in this triangle NCO, in triangle NCO, in this triangle, what is the exterior angle? I is the exterior angle, and it can be written as sum of alpha and gamma. So, I is equal to alpha plus gamma, right? Why? We can mention the reason here, exterior angle property. Exterior angle sum property. What is that? The exterior angle is equal to the sum of the interior opposite angles of a triangle. So the same reason applies here also, and we can mark this as 5 and this as 6, right? We can put the value from 5 and 6 in 3. Very important step. Put 5 and 6 in 3. What will we get? For R, I am writing gamma minus beta. Gamma minus beta. For R I have written, and N2 as it is. And for I am writing alpha plus gamma, and here as it is N1. Now we know that for small angle approximation, tan alpha is nearly equal to alpha, tan beta is nearly equal to beta, and tan gamma is nearly equal to gamma. So for small angles, tan alpha is equal to alpha, tan beta is equal to beta, and tan gamma is equal to gamma, right? So from this, therefore from 4 in 7. From 4 in 7, what will I get? For gamma, I will write Nm upon Pc. For beta, I will write Nm upon Pi. Multiplied by N2. And for alpha, I will write Nm upon Op. Plus, for gamma, I can write Nm upon Pc. Right. So this is what, and now this will be N1. I can take Nm common from both the sides. So this will be Nm, and here 1 upon Pc minus 1 upon Pi into N2 is equal to Nm 1 upon Op minus plus 1 upon Pc. This is N1. Now this N1 can be, Nm can be cancelled from both the sides. And what is Pc? Look at this. This Pc is actually the radius of curvature. So I can mark this distance as radius of curvature. Pc is radius of curvature and Pi is image distance. So I can mark this as image distance, right? And OP is what? This is the object distance, and Pc again is R, right? We have to apply the sign conventions also. So here Pc is radius of curvature, and this distance we will measure from pole. So from here to here, if I am measuring, from pole, that means I am moving this way. So this direction I am measuring, and the direction of incident ray is also this. So R will be positive. Yes. So this is plus R. Then we have to mark for Pi. Let's check what is the sign. We have to measure from pole. So we have to measure this distance from pole. So I am moving this way. Incident ray is this way. So both are in the same direction. So I can say that this is positive again. What else is left? OP. So OP is object distance. Let's check the sign. Now this is OP. I have to measure this distance from pole. Okay. I'll stand at this position, pole. Now I have to measure this distance. So I'll move this way to measure this distance. So this distance is opposite to the incident ray. So this will be minus, right? So this will be minus, right? We will put the values with the sign and then we will calculate. So this is our equation 8 and the sign convention values are equation 9. So from 9 in 8, put the values. Pc is R. So this is, let's multiply this also. 1 by R, N2 I am multiplying here, minus N2. Pi is what? plus V. So this is V, and this is equal to N1 multiplied here. So N1 upon OP is minus U, and N1 multiplied here, and PC is what? Plus R. Let's rearrange it. So I can take this N2 upon R minus N1 upon R is equal to N1 upon minus U. So I can write this minus over here. One and the same thing. This is minus N1 upon U or N1 upon minus U. One and the same thing. And this can be shifted this side. So this can be written N2 upon V. That's what we were supposed to prove. So let's change the sides, no problem. We are taking this on this side. So this will be N2 upon V minus N1 upon U is equal to N2 upon R minus N1 upon R. Hope there is no confusion. Instead of writing this here, we are writing the total thing on right side and the total thing on the left side. So simple rearrangement, N2 upon V minus N1 upon U. So this is again N2 upon V minus N1 upon U is equal to N2 minus N1 upon R. Very, very important result. Numericals are also asked from this topic, and the derivation as it is very important. They sometimes state this way. The question is asked this way. Find a relation between object distance, image distance, refractive index of the rarer and the denser medium, and the radius of curvature for a spherical refracting surface. Now to remember this, because you will require this formula for deriving some other concepts, which is Lensmaker's formula. So you can remember it like this. Refractive index of the medium where the image is formed upon image distance minus refractive index of the medium where object is kept upon object distance is equal to difference of the refractive indices upon radius of curvature. So this you can write it this way also. Refractive index of image medium upon image distance minus Ri of object medium upon object distance is equal to image medium refractive index minus object medium refractive index upon R. So this is a trick to remember, right? So this is what? This is a trick. So that you don't forget, because otherwise there are chances of getting mixed up with the suffixes. So this was all about the derivation of the relation between U, V, N2, N1 and R. This is called as refraction at spherical surface. That's all for now. Have a nice day.